Thank you. So this work is joint work with Laurent Mazet and Magdalena Rodriguez. And the beamer was prepared initially by Laurent Mazet. I'm not competent for this sort of thing. However, I was obliged to make many additions and changes. So everything that's bad in there is my fault in this beamer. Okay. What is a periodic surface? Well, let me try and give you a definition, and we'll see why one has to think twice about this. Consider a three-manifold and a connected surface S that's invariant by some discrete group of isometries, so that the quotient by the group is a smooth surface in the manifold quotient M over G. Then that's a natural definition of what periodic means for the group G. But keep in mind now that I'm thinking of this connected surface in the total space and the group leaving invariant the connected surface. The classical case that much work has been done on is flat three manifolds, R3, and the group is then generated by one translation, a singly periodic minimal surface or surface, two translations, three translations, or a screw motion. One can imagine a helicoidal surface. So the kind of groups that give rise to periodic surfaces in R3 are these translational groups and screw motion groups as well. There's another notion of periodic surface that's natural, and that's to consider an embedded surface in the quotient space M over G. So take some manifold, have a group act on it, suppose the quotient's a manifold, then you might ask, well, what are the embedded minimal surfaces in M over G? Or what are the embedded constant mean curvature surfaces in M over G? These two notions are not necessarily the same, because you can imagine a surface in M over G that when you lift it to M, it's not connected and invariant by the group. You can imagine a surface, for example, a small sphere in M over G, and you lift it up into the total space and you get many disjoint spheres. And the group does not leave invariant one connected component. So in that sense, there's two notions of periodic surfaces. And the natural notion that I'm going to talk about today mostly is a surface that really comes from a connected surface in the total space invariant by the group. Now it turns out that this distinction didn't come up in the past because in flat three manifolds, the two notions are the same. If you take a flat three manifold, then whether you look at a surface in the quotient, the covering space, which here is R3, invariant by the group, or whether you, a connected surface, or whether you look at the surface in the quotient, except for parallel planes, the two notions are the same. Any surface in the quotient, R3 over a group of translations or screw motions, etc., lifts to a connected surface in R3, except if the surface is parallel planes. And that's because of this theorem of Hoffman and Meeks that if you have two properly immersed, disjoint, minimal surfaces in R3, then they're parallel planes. But as soon as you start looking at other manifolds, this is no longer true, so one has to distinguish between the two notions and what you're talking about. Now, in periodic surfaces in R3, there's been a great deal of work. And Meeks and I proved the following theorem, that if you look at properly embedded minimal surfaces in flat three manifolds, then they have finite topology if and only if they have finite total curvature. And moreover, you can say exactly what the geometry of the ends are. The ends are either asymptotic to flat planes, or they're asymptotic to parts of helicoids. So you have a complete understanding for the flat three manifold case of the geometry of periodic minimal surfaces. This formula here, it's not usually written that way, but it turns out that when one's thinking about other three manifolds, it's better to think of the formula like this. Let me be a little more precise. In R3, the square of the second fundamental form is equal to minus twice the intrinsic curvature of the surface. Now, in general three-manifold, this is no longer true. And in R3, one usually writes this formula as the total curvature in this sense of the Gaussian curvature, the intrinsic curvature, is equal to 2 pi, the Euler characteristic, minus the winding number. And when you write it this way, then you're seeing a Gauss-Bonnet type theorem. If you forget this winding number here, then this is just the Gauss-Bonnet formula for a compact surface without boundary. But it turns out that this formula for properly embedded minimal surfaces in flat three-manifolds of finite topology really tells you a great deal about the surfaces. However, but in other three-manifolds, it's not the intrinsic curvature that's important, as we'll see shortly, I believe, but the shape operator. And once you think about the integral of this over sigma as being the important invariant to study properly embedded minimal surfaces in other three-manifolds. Now, let me show you what the structure of this periodic surfaces is in R3, because this is what we're going to do in the hyperbolic plane cross R. So classically, how does one make periodic surfaces? You take some nice geodesic polygon, and you look at a least area disk with that boundary, so a solution of the plateau problem. And people knew for many, many years that if this polygon has the property that there's a killing field in space, I'll call the killing field in R3, it's just the vertical killing field d dt, where this is the t coordinate. If there's a killing field in space such that the Jordan curve you're looking at is a graph over some surface by this killing field, here it's the boundary, for example, here could project to a square. And if this curve here is convex, then there's a theorem that says there's a unique compact minimal surface with this boundary, and it's a graph. It's a disk, and it's a graph over this domain. That's a very beautiful theorem that was originally proved by Rado in R3. But this theorem works in three manifolds when you have a killing field. When you have a killing field Y, and you have a Jordan curve that, with respect to this killing field, has a nice projection onto a surface which is convex, then you can say there's a unique minimal surface with that boundary that's compact, it's embedded, and it's a graph. And that is a very, very important structure, because being a killing field and a graph with respect to the killing field means one has curvature estimates. It means that this surface is stable, and there's a lot of understanding of the geometry of stable minimal surfaces. So just from an elementary point of view, you start off with some polygon. You have some killing field for which this polygon has a nice projection onto some surface that's convex embedded curve. And immediately you know the structure of all compact minimal surfaces with that boundary. Moreover, they're topologically a disk, they're graphs, you have nice estimates. Well, then Schwartz observed that when you have ambient isometries and you have a polygon such that the edges of the polygon admit rotations by pi about the edge, then you can extend the minimal surface by this rotation. So here you have a geodesic, a straight line. You have an ambient isometry, which is rotation by pi about this. And Schwartz reflection says that this minimal surface extends smoothly across that edge. So you can keep on going. Here's another edge. You can extend smoothly across that. And Schwartz was able to construct many, many interesting minimal surfaces by doing this. Etc. And if you just think of what I've just done here, what does this have to do with periodic surfaces? If I started off, example, with 1, 1, and this was a square, then this surface that one constructs is invariant by translation by 2 unities this way, translation by 2 unities coming out of the blackboard, and translation by 2 unities going up. It's invariant by the group of translations of these 3 independent translations. The group in question has a quotient as a 3 torus, and you have a periodic minimal surface in the 3 torus, R3 over Z3, which is topologically a surface here of genus 2, or genus 3. We'll see in a second, whatever that case may be. So, Schwartz was able immediately to construct minimal surfaces like this. Let me show you the Schwartz surface. This is a picture drawn essentially by Schwartz many years ago, where he started off with the polygon here that's this quadrilateral. It's a fourgon. You solve the plateau problem. You get this embedded minimal disk that's a graph, and you do all the symmetries, etc. This is a triply periodic Schwartz minimal surface. And Schwartz, when he drew this, amazingly enough, he didn't have computers at the time. It's difficult to understand how he did this so well. He observed that this fundamental piece here fits in a cube, and this curve of intersection here that you have here, 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 you have 6 curves of this nature, is very, very close to a circle. It's not a circle. But this looks like what you get from a cube when you take the one skeleton going from the midpoints of the faces and thickening it to a tubular neighborhood and taking something that realizes a minimal surface by just thickening enough. You start off with big mean curvature, thicken, 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 you get 0 mean curvature. So this was Schwartz's, no, I went too fast, Schwartz's surface. Now, this is a triply periodic minimal surface. Another construction that is a 3-manifold construction, not just R3, is the following. So we started off with this square, say, and we took 1, 1, 0, 0, and we got what we drew right here, this graph. So it's natural to try and take here plus n, minus n, minus n, plus n. Let n go to infinity and see if there's a limit. And Shirk observed that this could be actually written down as a formula. The limit exists, and it's Shirk's surface, and it's bounded by 4 vertical lines, which you see on the cover of, for example, Manfredo's book. And this surface has a formula log cosine x over cosine y. And now you can do the rotations by pi about the 4 lines and extend this surface to a properly embedded periodic minimal surface in R3 that's doubly periodic. It's going to be invariant under, it's a graph here, it's a graph here, it's a graph over the black things in a checkerboard. So you get something invariant by Z2, this translation and this translation. And that, well, actually, no, this was this surface here, because I had straight lines here. I didn't go to infinity. But if you go to infinity, you see that you have, oh, no, this is another surface, the Cauchy saddle surface. This is an example that's much of another nature, more difficult to construct. It was constructed by Cauchy. If I start off with 2 squares like this, then if these are close enough in space, you can imagine that there's a minimal surface there that's like a catenoid, like this. If they're too far away, this doesn't exist. But one can actually show that this exists if you take this to be bigger, etc. You can pass to the limit and get 4 vertical lines and show there's a minimal surface which has the topology of an annulus that's bounded by those 4 vertical lines. And then you can get a global periodic surface by doing all the rotations by pi about the 4 vertical lines to get a doubly periodic minimal surface, and that's this surface here. So you see, here's the 4 lines. Imagine that going up to plus infinity. Here's the handle. You do all the symmetries. You get this doubly periodic surface. Okay, now what I'd like to do is show that one can do constructions like this in other spaces. And just show you many examples, many things that happen. And then we just point out that this is the first paper I know of in this subject. So it's an elementary talk I'm going to give you. As far as I know, nobody's really studied periodic surfaces before in spaces aside from the space forms like R3, S3, etc. But I'd like to convince you that it's very interesting to look at periodic surfaces in the hyperbolic plane cross R. So I'd like to show you there are very nice examples and there are theorems. And just point out that the subject is really open. It's just the beginning. So the isometry group of H2 cross R is much bigger than that of R3. And we're going to look today at essentially a few groups. We'll look at the group generated by a vertical translation along the t direction by H. That'll give singly periodic surfaces. We'll look at the group generated by T of H and phi, where phi is a translation in the hyperbolic plane along a geodesic. So this phi will always, if I think of the disk as the hyperbolic plane, then I'll fix a geodesic here, gamma 0, and phi will be translation along this by some fixed quantity, say a distance 1 for the moment. And the geometry of this translation is important to understand. If I look at this, then the equidistant curves here are circles, d of s. They're invariant by this isometry. These are in the hyperbolic metric, this is the curve of distance s from this geodesic. So this is a geodesic here. This is distance s, s, s. So we have this foliation by the equidistance. They're invariant by this isometry. And I call them d of s. So if you quotient H2 cross R by T of H and phi, this group is isomorphic to Z2. These two diffeomorphisms commute. One is horizontal, the other is vertical. It's really an action of Z2. So it's a doubly periodic surface that you're constructing. And we're interested in constructing finite topology embedded minimal surfaces in that quotient. We'll call them doubly periodic minimal surfaces. The other group, the last group we'll look at, is groups that come from isometry groups of H2, which give a tiling of H2. So that's a very, very rich class of groups. There's no Z2 subgroup there. There's Z subgroups. There's free subgroups. And there's many, many subgroups of H2 that give tilings of H2. And you can consider what are the embedded minimal surfaces in the quotient of H2 cross R by such groups. Those are called, we'll call those tiling surfaces. Let me just mention the geometry of the space, the doubly periodic space. If I take an equidistant to this geodesic that we're translating along gamma 0, d of s, so this distance here is s, this is d of s. This is invariant by the isometry. If I look at d of s cross r, so that's R2. I can quotient this by the group G generated by T of H, translation by H, and phi. This is a torus. It's a torus, T of S. What kind of torus is it? Well, the geodesic curvature of this curve, this equidistant curve, is given by hyperbolic tangent of S. If I take the product of that with R, I get a constant mean curvature surface whose mean curvature is hyperbolic tangent of S over 2. So this torus has mean curvature hyperbolic tangent S over 2. When S is 0, that mean curvature is 0. It's totally geodesic. It's this gamma 0 cross R, quotient by the vertical translation and the translation phi. So this space, this quotient space here, looks like metrically like this. This is T of 0. This is T of S. On the other side, we have T of S2. This is S here also. Here the mean curvature is 0. Here the mean curvature is between 0 and a half. And as you go to infinity here, the mean curvature goes to 1/2. It's always less than 1/2, it goes to 1/2. So we have a space here which is differentiably just T2 cross R. But metrically, it has this structure where the area of these tori is growing exponentially. This vector field here, which is geodesic vector field, orthogonal to this foliation by equidistance, this vector field Z, passes to the quotient here, Z, and if you go distance S along the orbits of this geodesic, you get to T of S. So the structure of this space is pretty metrically. You have a foliation by these tori of constant mean curvature. It starts off at 0, it goes to 1/2. So what are some examples of constant mean curvature or minimal surfaces in that space? Okay. The first examples you can take come from the quotient of a cylinder in H2 cross R. If I take H2 cross R, here's the disk cross R. If I take a small circle here, I pick the product with R. So that has mean curvature bigger than 1/2. It's a constant mean curvature cylinder. If I make that circle small enough, then I can put it in a fundamental domain for this group, and in the quotient it becomes a torus here of constant mean curvature bigger than 1/2. So you have in this space this torus of constant mean curvature bigger than 1/2. I could also take a delta A that has period H. That's constant mean curvature 2. And if this is period H, it passes to the quotient, you get another torus of constant mean curvature H. I could also take a rotational sphere of constant mean curvature H if it's small enough. That'll pass to an embedded surface in the quotient. So those are examples of surfaces which are not really periodic because the group doesn't operate on this and leave it invariant. When you do the translation by phi here, you get another disjoint sphere. So this is not periodic in the really strong sense, but it's an embedded constant mean curvature surface in the quotient. And then you have these tori. So we have a theorem. In three manifolds, or in R3 say, Alexandrov proved an embedded compact constant mean curvature surface is a round sphere. That's called the Alexandrov theorem. So a natural question in other three manifolds is, what are all the embedded compact constant mean curvature surfaces? In the space forms, we know that they're all round spheres. It's a theorem that in H2 cross R, the compact constant mean curvature surfaces are rotational spheres. They're rotational spheres. But now what about the quotient here by this doubly periodic group? What about this space T2 cross R with that metric quotient? Well, one has this theorem of Laramazze, Magdalena, and myself. Suppose you consider a compact embedded constant mean curvature surface, then one has the following possibilities. It's a torus T of S for some S, so that H is less than 1/2. It's one of those equidistant tori. Or it's a rotational sphere, H is bigger than 1/2, so it's one of these quotients. Or it's a quotient of a vertical del and A. For example, it's quotient of that. There's another possibility that comes up. The other possibility that exists is it's a bigraph with respect to this Z vector field here. Here's T0, this torus, totally geodesic. I have the Z vector field of geodesics orthogonal here, Z. One can consider a surface which is a graph with respect to Z on this side and a graph on this side and orthogonal to T0. So it's sort of like this. Here it's transverse, here it's orthogonal, where it intersects T0. It's a Z bigraph. For example, if I take a geodesic of T0. T0 is totally geodesic. The induced metric is flat. It's just a flat 2 torus. So a geodesic is just a straight line. If I take a straight line on this 2 torus, then if I take a tubular neighborhood of it, that would be a Z bigraph. So here, I imagine this geodesic. A tubular neighborhood of it would be like this. It would intersect T0 in 2 geodesics. However, that tubular neighborhood doesn't have constant mean curvature because this metric is not a product homogeneous metric. But there's a theorem of Mazeo and Frank Paccard that says that given this geodesic, one can find constant mean curvature tori that are in a tubular neighborhood of the geodesic. And those tori are Z bigraphs. They have constant mean curvature, they're embedded. So there exist these examples. And one has this theorem that says that that's all the examples that there are. Now, there's another very nice space that I didn't mention yet, but I'm going to mention it now. Instead of taking a translation phi along a horizontal geodesic, one can take a translation along a horocycle. That's a nice isometry of the hyperbolic plane. And one has the following. So here's the hyperbolic plane. Take some point at infinity, take all horocycles, and take now some translation of hyperbolic plane C along these horocycles. Horocycle translation, it's isometry. And now I can look at the group generated by vertical translation and see. That's Z2, these two commute. It's a doubly periodic space. It's also differentiably T2 cross R. If you think of this horocycle cross R quotient by the group, you get a torus. So here you get tori T of S. Let me call this horocycle here C of S. C of S cross R, modulo the group, to 2 torus. What is its mean curvature? It has constant mean curvature. This horocycle has curvature 1 in the hyperbolic plane. The mean curvature of the product with R is 1/2, because the other principal curvature here is 0, so the average is 1/2. So this has mean curvature 1/2. For any horocycle, it's the same constant mean curvature. And now the Z vector field also passes to the quotient, but these are all geodesics that are asymptotic at infinity. This is distance S. It's constant along between 2 horocycles. And now the quotient space metrically looks like this. T of S1, T of S0. There's the vector field Z. We go distance S here. And they all have mean curvature 1/2. Consider that quotient space for the moment, and you can ask the same kind of question. What is the Alexandrov theorem in this quotient space? Okay? Okay, so this is a discussion of that space. So this is a theorem of Ana Maria Menez that says the following. Suppose you take a compact embedded constant mean curvature surface in this space, this doubly periodic space. Then it's either one of these torus T of S that has mean curvature 1/2, or it's a rotational sphere. You can quotient the rotational sphere of H2 cross R, or it's a quotient of a vertical undulate. So this classifies, now there are no bigraphs. This classifies all of these surfaces. I would have liked to have given an idea of the proof. It's very pretty. When did I start? I'm supposed to stop at 10:30. Yeah. I won't give an idea of the proof. Sorry. Because I want to give you examples, and I haven't given you any really interesting examples yet. So there's a very nice proof of this. It's a pretty theory. Okay, so let me start beginning to construct some examples. So I have the disk model for the hyperbolic plane, and this picture is going to be important for the examples. So let me put some parts of that picture here. And the parts I'm going to put are, we have the geodesic gamma 0. We have the geodesics orthogonal to that. If I fix the origin here, 0, 0, in the Euclidean disk, and I call this hyperbolic distance mu, I'll fix these two geodesics, g of minus mu, g of mu. And then we have these equidistance d of s here as well. That's all we need for the moment. Let me point out that we have these other geodesics here, gamma theta, this angle theta here, this geodesic gamma theta. And we'll talk about that in what comes up. Okay? So we have y theta, which is a killing vector field, which is translation along gamma theta. For any of these geodesics, you have hyperbolic translation along that geodesic. That's a killing field. I have z, this vector field orthogonal to this, gamma 0. That's not a killing field. The flow of this z does not produce isometries of the hyperbolic plane. Okay? Then we have T of H. So an immersed surface is a graph with respect to a vector field if the vector field intersects it in at most one point. So I can talk about y theta graphs. Y theta is the killing field, which is translation along this geodesic. I can look at graphs with respect to that killing field. This is very useful because what I said in the beginning was, if you want to construct surfaces, take a Jordan curve, solve a plateau problem. If that Jordan curve is a convex graph with respect to a killing field, you know automatically the solution to the plateau problem is unique and it's a graph. So it's a disk. It's embedded. There's no other minimal surface. And since it's a killing field, you get stability. So that means if you vary the boundary values, you vary the minimal surface continuously. So you can start varying the boundary values, and you have a unique way to continue the minimal surface. That's why it's important to talk about graphs with respect to killing fields. And I already defined what a bigraph was, so we don't need that. And a vertical bigraph, well, that's clear. It's a graph over a horizontal H2. Okay. So I want to construct examples that are interesting. Okay. So there's two types of asymptotic behaviors we'd like to consider. The quotient of G by a vertical plane, so take G of mu cross R. That's a totally geodesic vertical plane. It's minimal. And you can imagine a minimal surface that's asymptotic to that in the quotient. That's one type of asymptotic behavior. The other interesting asymptotic behavior is asymptotic to a horizontal slice. So I have H2 cross R here, and I can imagine the quotient being asymptotic to a part of a horizontal H2. So that's like in R3, you're asymptotic to a plane or to a helicoid. But here I'm interested in surfaces with that asymptotic behavior. So let's start off with beginning the first non-trivial example. It'll be a horizontal Schur-type surface. So you should think of the doubly periodic Schur surface in R3, and I'll start off with a certain fundamental piece. The fundamental piece will be bounded by 4 horizontal geodesics. The geodesics will be G of minus mu cross 0, G of minus mu cross H, G of mu cross 0, G of mu cross H. And the surface is going to be asymptotic to 2 horizontal ends and 2 vertical ends. So what is this surface? I'll start off by taking a polygon, a compact polygon, and solve a plateau problem. Okay? What is the compact polygon? Here, I have 4 points. So here's G of minus mu at level 0. I go a distance r here, call that A of r. Go a distance r here, hyperbolic distance, B of r. And here, C of r, D of r. So I have these 4 points. Okay? So there's A of r, B of r, C of r, D of r. I take 4 geodesics. That's part of G of minus mu. That's part of G of mu at height 0. Then I go up to height h and do the same 2 things. But now I join them by 2 vertical geodesics. Those are geodesics of H2 cross R. And on the right side here, I take an equidistant curve to join C of R to B of R. And I translate it at height h. So if I drew that as a Euclidean polygon, I'd be drawing something like this. That would be the Euclidean picture. But now, these are hyperbolic geodesics. That's an equidistant. And in the Euclidean case, we already discussed this. The solution to this problem here was the first surface I drew today, but rotated by pi over 2. I made the picture vertical to begin with. Now it's horizontal. Okay? So you have this surface here. And this surface, so it's a minimal disk. It's embedded because it's a solution to the plateau problem for an embedded Jordan curve. And sigma r, you call it solution. Now we'd like r to go to infinity, and we'd like A of r to go to this point at infinity, and D of r to go to the other point at infinity. And we want to see if there's a limit. And what is that limit? So we want to control the limit of this. Now, there's one thing to control easily on the left-hand side. As r at this point goes to infinity here, I can call this point here A infinity, this point D infinity, and look at the geodesic of hyperbolic space between them, beta. That geodesic is orthogonal to the boundary. If you think about it, this geodesic cross R is disjoint from that surface. It's outside of the convex hull of the boundary. So it's for any R, this geodesic that goes here to there is disjoint from this whole surface. So as R goes to infinity, that surface cannot go to the left of this geodesic. As R goes to infinity, the surface cannot go here. What happens here as R goes to infinity? Here the equidistants are going to infinity, so maybe the whole thing goes to infinity and disappears. Well, amazingly enough, we construct a minimal barrier here. I won't give the details. That is a minimal surface that comes in like this. This depends on the fact that h is bigger than pi. To make this construction, we need h bigger than pi. So if h is bigger than pi, did I say this anywhere? Not yet. One can put a minimal barrier here to... Okay. So what I'm saying here is that when r goes to infinity, one can control the limit because of stability. You have curvature estimates, you have unique solutions, so when you vary the plateau boundary continuously, the solution varies continuously, and you can manage to show there's a limit. There's no picture of the limit. So if h is bigger than pi, there's a barrier on the right-hand side. And using these barriers and curvature estimates, you can show that this converges to a surface sigma infinity. Now this surface is bounded by 4 horizontal geodesics. G of minus mu, G of mu at height 0, and at height h. Now think of this surface, because I had a lot of trouble imagining this could exist for the following reason. This surface is bounded by, this is the geodesic at height h going to infinity. This is the geodesic at height 0, height h. This goes to infinity, okay? And now we have the same thing, G of minus mu. How am I make this picture? I have a picture like this. No, let me try that again. Like this. Now this surface has these 4 geodesics as boundary. This is at height h, height h, height 0, height 0. And it doesn't disappear on the left, it doesn't disappear on the right. It's a connected surface with this boundary. What does it look like? What it looks like is the following. It's asymptotic here to this vertical strip, and here it's asymptotic to the horizontal slice. Here it's asymptotic to this and this. Just the way in the Euclidean case, you would be asymptotic to, see in the Euclidean case, let me draw it vertically. I'm so used to doing this. I'm asymptotic to this vertical strip, and then this vertical strip this way, and the one in the back. But in this case, what's really amazing is this vertical strip is Euclidean. It has linear area growth. This strip here on this side has exponential area growth. This is H2 cross H. It's a hyperbolic plane. So this minimal surface has exponential area growth here, linear area growth here. It seems like it shouldn't exist because it's not in equilibrium. However, it exists, which is really something that surprises me. Okay, let me, yeah, you're right. Okay. I'm not going to be able to, let me just mention that another technique to do construction of surfaces is this conjugate surface construction. You solve a plateau problem for a polygon. By your choice of the polygon, it's a vertical graph over a convex domain. This is a geodesic, geodesic, geodesic. And in H2 cross R, just as in R3, one has the notion of a conjugate minimal surface. In R3, if you take a minimal surface, you have a one-parameter family of isometric minimal surfaces, going, for example, from the catenoid to the helicoid. In H2 cross R, this isometric deformation exists also. This is a theorem proved by Hauswirth, Tubiana, and Saerp. And they proved something much more useful, that if you start off with the surface that's a graph over a convex domain, then the conjugate surface is embedded. The conjugate surface is a graph, not over a convex domain, but it's embedded. So here, if you start off with something that's a graph over a convex domain, and you take the conjugate surface that's given abstractly, it's very hard to control this conjugate surface, what you do is, you get an embedded surface. And then, knowing the boundary that you started with, the conjugate surface, you control the boundary of the conjugate surface, just as in R3. There's work to do there, but it works. Let me just... So, here, I don't know if you can use your imagination, but This is part of a horizontal geodesic. This is a curve along which this surface is orthogonal to this vertical plane. This is a curve along which the surface is orthogonal to this vertical plane, making an angle pi over 2 with this vertical plane. So here I have it's orthogonal, orthogonal. Here it's orthogonal to this horizontal plane. Now you have these symmetries. When it's orthogonal to a plane and minimal surface, you just reflect along the boundaries. So just do reflection along this plane, along this curve. It's orthogonal here, go to the other side. This geodesic goes to a geodesic here. This curve goes to half of something that looks like a circle. So let me just finish by a picture of what that would give you. When I take that, what one is going to construct is the cautious saddle like this. This is the piece that one is looking at here. This is the geodesic going off to infinity, goes off to infinity. This is orthogonal to the boundary. When you do the symmetry here, you go off to infinity here. And here you get this circle here. You do symmetry in this plane, it goes down. You do the symmetry across this side. And you get, in Euclidean space, it would be like this, asymptotic. But the point is now you can take all these symmetries by these four geodesics that are horizontal, and when you do the rotations by pi about the four geodesics, you get a doubly periodic connected minimal surface in the quotient space. It comes from a connected surface in H2 cross R. This is really the doubly periodic Koster saddle in H2 cross R. And I'll just stop with this picture here. This is an example of a tiling surface that I said that another very interesting group is take any subgroup of the isometry group of H2 that acts to give a tiling of H2 and construct embedded minimal surfaces in the quotient there. There are many interesting examples, much more so than we have begun to analyze. And here is the simplest non-trivial example that one gets, which is a bigraph over the domain that you obtain from this by doing all the symmetries here. It's a bigraph over that. And this dotted figure here, this is a semi-regular polygon of the hyperbolic plane. A regular polygon is a polygon where all the sides are equal, and the angle here would be pi over 2. If this angle is pi over 2 here, you can do all the rotations about the vertices and get a tiling. Semi-regular means this side has a different length from this side, but the angles are all pi over 2. And when you do all the reflections, you get a tiling of the hyperbolic plane. So one can construct many interesting periodic minimal surfaces in that quotient. Okay, I'll stop there. Thank you.